it gives me a great deal of pleasure to introduce today's speaker. So Pranay and Titus were the two latest hires, and essentially these were the people along with some of the older guys who makes us one of the best condensed matter theory groups in the country.
Arguably,
there's no arguably there now. There's no arguably there anymore.
Being politically correct.
Yes, that is being politically correct. Yeah, but we are probably the best condensed matter theory group in the country now. From there, he went off to another high-powered place in France, Toulouse, where he was a joint postdoc with Fabien Allais and Sylvain Capone. Then, after drinking so much good red wine or French wine, he decided that he needed some good German food and decided to go to Max Planck Dresden, and which is one of these other high-powered places where he worked with Marcus Hale, but this time working on dynamics. So once he had finished his stints in Europe and America, then he decided that he was to go to the Far East, went off and started working with Nick Shannon and his high-powered group studying frustrated magnets, and by then we were lucky enough to get him back to IIT Madras as a faculty. So I'm not going to stand between him and a fantastic talk. So Pranay, the floor is all yours.
Clapping before the talk. Okay, thank you, Professor Narayan, for the very kind introduction. I think I can safely skip my first slide after that introduction. I think it has less info. Narayan mentioned I did my bachelor's and master's here, and is my master's thesis advisor. We worked on a problem related to classical glasses, which was later taken up by Shashi. I was a student in the group who finished his PhD, I think in 18 or so. And then I went to Boston University, where my thesis topic was phase transitions in quantum spin systems. I'll talk about that today. And then three postdoctoral positions, and then finally I'm back here. Just joined 2 months ago. So I wanted to thank the committee, Professor Prabha and Professor Nirmala, for giving me the opportunity to present my work over here. So I'll just go through my research interests, and then I will just discuss snapshots of different projects that I've done, so that it gives you an idea of the fields that I'm interested in, and then I hope we can build some collaborations from there. Okay, so yeah, broadly I'm interested in condensed matter physics, but mostly as a playground to explore statistical physics problems where statistical physical principles come into play. So I'm not quite stuck to magnetism, but I'm just in general that turns out to be an arena where there are a lot of interesting models showing a lot of interesting physics which is universal. And of course there's also relevance for quantum information and computing, and a lot of the concepts carry through to this field as well. So I'll be talking a little bit about that as well. Okay, so motivation. This is a very from an article by Professor Bhaskaran, a very nice illustration of Anderson's garden. So this is P.W. Anderson, and these are all different illustrations of the concepts that he invented / developed. Many of the condensed matter people might recognize Anderson localization here. This is probably the quantum Hall effect, and then resonating valence bond physics, and so on. So one of the one of his very nice contributions to popular physics was to write this article, which is called "More is Different," which was trying to sort of show people that it's not, physics should not be just about going smaller and smaller, but there's also interesting new things that appear when you go larger and larger. And this is a very nice article which I would recommend everyone to read. Probably many of you already read it. It's only 3 pages, and it's very accessible at all levels. So I'm going to be talking about effects which are unique to collections and not really possible for individual objects. Right? So there's a huge number of them, which is why condensed matter physics is such a large arena, and I just cannot list everything in one presentation. So I'll just talk about those which I have touched upon during my research. And also it's very instrumental, because once you talk about these ideas of statistical physics, They are unique irrespective of which subsection of physics that you're considering, because the same mathematical structures like field theories, they apply all the way down to materials, magnets, and then all the way up in high energy physics and to astrophysics and so on. Okay, so yeah, and I'm also interested in exploring both the equilibrium and out of equilibrium physics, and I'll be talking about examples from both fields. Okay, so just to give some motivation about where this sort of emergent physics is important, or physics at scale is important. So I'm sure many of you have seen the Ising model. The Ising model is a very simple toy model for magnetism, but not only for magnetism, actually it can be used for everything. I heard in a talk from established researcher in condensed matter that if you, the thing that he tells people if they want to understand the Ising model is QR codes, because that's something that we see everywhere, and QR codes are basically just configurations of the Ising model, because there are two options, they are either black or white for each square, and that's an Ising model at very high temperature, because they're mostly completely uncorrelated. So the Hamiltonian is very simple. It's just trying to align spins together. So if you are at very low temperatures, you can imagine that all the spins align together, and at high temperature you can consider them to be all completely random, right? Okay, but now if you look at the system at different scales, so this is the system at 256 by 256 lattices. So this is a relatively large system, and this is 64 and this is 16, getting smaller. If you look at these, these are at different, the columns are at different temperatures, right? And you don't see much of a difference, in the sense that you can't say anything systematic when you look at this. But as you go to larger sizes, over here you see something emerging. You will see that everything below TC more or less looks as if it is one color, whereas everything above looks completely random. And at TC you will see these very large structures which are related to the correlation length. And this is something that's apparent only because you're looking at something that is large, in the sense that you can't really make this distinction for smaller sizes. Right? So that's something that is inherently observable only when there is a large number of objects rather than a small number of objects, right? Okay, so now, so that's just a very well understood example, and now I'm going to be talking about more modifications of this which are a little bit more involved. So this is so let me just go back to the Ising model. For the Ising model, this was just a scalar. It can just be +1 or -1, right? Now let me consider a spin that lives in a plane. Okay, so it can point in any direction in this plane, and for some reason, let's say that it's only allowed to point in certain discrete directions. So 0, 1, all the way up to q -1. So q options. So this is motivated from spins that are in some sort of crystal field which is breaking the symmetry and forcing some directions to be more favorable than the others. But a very nice example comes from hexagonal manganites, which are compounds that have these atoms. The oxygen is the mobile atom over here, relatively mobile. And once you look at these structures, the oxygen is pulled to one of its neighbors, and it can be pulled in 6 different directions. So that gives you a 6-fold degeneracy, right? And this is a structural distortion which you can measure just by looking at the polarization, because the direction in which the oxygen is getting pulled is telling you the polarization. So this 6-fold degeneracy has been seen in experiments, and you can see, so these different domains are called alpha plus, beta plus, and so on. There's some nomenclature for that, and once you take snapshots, you see that these different domains are existing in the sample, right? And at very low temperatures, you can assume that one domain will dominate, because it's expensive to have domains that are next to each other which are not aligned. So one domain will dominate, so the entire magnetization, the total magnetization, will pick one of these directions. Plotting the total magnetization as a histogram, and if you look at this, so this is low temperature, this is high temperature. Okay, so temperature is increasing like this. Okay, so this is low temperature. At low temperature, there are 6 possible options, and the total magnetization, which is the sum of all of these small patches, is falling into one of them. Right? At high temperature, you can assume that this guy doesn't really care about what this is or about what this is, and so on. So everything is completely random. So you're summing up random vectors. So the result is just 0. and that's what you get at high temperature. And intermediate, something very interesting happens, is that you actually get the magnetization pointing in all possible directions, not just one of the 6 directions. Right. And this is really really an interesting phenomena, because individually, if you looked at the individual microscopic objects, these hexagons, they can point in only one of the 6 directions, but together they are able to do this, which is beyond what a single microscopic object can express. Right. So this is why we refer to it as an emergent circular distribution. And this is just an example. This is a very simple example. You can get you can actually change this Q. Instead of having 6, you can have 8, whatever you want. Anything greater than 4 does this. And you can also go beyond just being stuck on the plane. You can go to the sphere or to higher objects, and you also get this. So this is something very striking, right, about what these systems can do. Okay. Another thing is fractionalization of spins. So we know that if we take an electron, it has some quantized spin, right? The spin is given by what? Spin half. Now, localized electrons on something like this lattice. This is called the Kagome lattice. It's just it's from a Japanese basket pattern. This is not just fiction, because it has been realized in Herbert Smith that actually Professors Khuntia and Setupati have studied this, and in this paper. And this is very interesting, because the Hamiltonian is just SI dot Sj, so it wants each spin to be opposite to every other spin. But if you look at a particular triangle, this is not quite possible, because this is opposite to that, then this cannot be opposite to both of them. Right? So these are called frustrated magnets, and this Hamiltonian can be rewritten as a sum over all the possible triangles, all these small triangles, and inside and for each triangle you take the sum of all the spins squared, and this is what you want to minimize. Right? So this is minimized by setting each of these to be 0, because there is a square here, right? So this can only be 0 minimum, and there are of course many ways to do that, because if you have 3 spins, if you just want to add them up so that they're 0, you can do, of course you can do that in many ways. So there's some degeneracy. Now if I call each of these things as a triangle, so let's say that the sum of these 3 spins on this triangle is given by a of this triangle. This should be 0, right? But the question is, are these independent variables? So let's look at 2 neighboring triangles. So this one and this one. So this involves these 3 spins. This involves these 3 spins, and there's one spin common, which means that the A triangle for this and A triangle for this are not strictly independent, right? Because they are sharing some information. But the number of ways to actually satisfy this constraint is so high that you can get away with saying that these are independent variables. And then something very interesting happens, because each triangle is carrying, each spin is actually broken into 2 triangles, right? Because this spin is shared by this guy and this guy. So this carries a total of 3 times half the spin. Right? Now if I take one triangle which has basically 2 missing sides, then this is half a spin. Right? And now if you look at the entire system and you study its response to magnetic field, you find that it behaves exactly like half a spin would behave. Now this is fundamentally not possible for an electron. Electron will behave exactly as spin half, right? But this entire object is starting to behave as spin quarter, right? And this is also something that is simply not possible, because you can't break the electron spin further, right? But because you're considering this, it's starting to it behaves as something that is emergent, and this thing becomes more exact as this system becomes larger and larger. This is another example of. So now moving into, so till now everything I was talking about was just with classical spins. Now if we move into the quantum realm, one of the simplest magnets is the Heisenberg chain, Si.Si plus 1, which is just a chain. It's realized in this compound. There's been imaging studies of this which show agreement with the theory, absolutely perfect agreement with the theory. So here, just understanding the ground state of this is already very tricky, because if you think of them as classical vectors, if you want to minimize this, you go with this configuration, right? This is up down, because this just wants to minimize the dot product. So you just do opposite spins. But if you look at just 2 of these and you write them out as operators, you diagonalize the Hamiltonian and so on, you find that the ground state is this, which is a singlet, which is up down minus down up, right? Now, and the triplet is, one of the triplets is up down plus down up, right? Now, and if you just want to consider one of these states like up down, that is this plus this, right? Okay, so now it's not clear, because this is not an optimal solution, because it's violating the ground state of a single bond. This is not an optimal solution because it's actually missing some bonds in between. So the question is, what does the system settle down to? And it's very interesting because the system actually settles into something that's in between these guys. And the way it does that is that it forms a 4-dimensional vector where 3 of the components are the spin and 1 component is a dimer, and this entire thing can be thought of as a 4D vector. And now if I look in space-time, so usually one just considers space, but you can also just go into the path integral language and talk about space-time. There, if you look at the spin, wherever the spin is bright, the dimer is dark, right, and vice versa. And that's just because you want to conserve the length of this vector. This vector. Yeah.
I think I missed something. So how do we form the dimer?
So the dimer is just the expectation value of this guy.
Or this?
Yes. So yeah, and these things you can infer from correlation functions. If you look at cross correlation functions of SI with D, then you get these diagrams. Yeah. Yeah, and then you can also do much larger objects. For example, we were talking about just SU2 spins, right? Or classical spins, which are O3 vectors or O2 vectors. You can actually do much larger if you look at SUN physics. Now, SUN physics, many of you may not be familiar, but it's the idea is very simple. We had O3 vectors, right? You make it instead of 3-dimensional, make it n-dimensional, where n tends to infinity, and then actually calculations become very easy. And this is a trick that theorists use all the time to do analytical calculations. Actually, for this result was a paper by Professor Damle, where they use the large N expansion to understand this, to actually derive this result. So yeah, so SUN physics is very interesting, and it's also.
That was too quick. So
which one? This one? Yeah.
So what are they? Is that what are they measuring?
Yeah, so this is from simulation,
Yeah.
and yeah, so some of this has, I should have been careful about this, but yeah, so this is the magnetization of the spin that is called the orphan spin. It's called the orphan because in this triangle there are 2 guys missing, and so that's the one. And this is as a function of Hs by T, which H is field and T is temperature. So this is the response.
So the response of that orphan.
Of that orphan spin, yeah.
Orphan spin.
So that instead of behaving like a full spin half, it behaves like a spin 1/4 almost, and that's because the neighbors are suppressing the magnetization, and that's not just the neighbors, actually the entire structure is doing that. Yeah. So if you go to high temperature, then you go back to a single spin, which is this curve, and as you can see, as the temperature is increasing, you go to that.
So as a whole, you are looking at this problem as each triangle represents a collective spin state, and
yes,
collective spin states are interacting among each other.
Exactly, yeah. And when you knock out 2 spins, then the collective spin inside this is just half, because half of this is in that triangle, and which is why it does this. So finally, the ground state can be understood as a triangle for every other triangle other than the defect triangle is 0, and for the defect triangle is half, and that behaves as a free spin off. Yeah. Yeah. So coming to the SU4 case, so this is engineered using trapped ions, where now there are a number of experimentalists also in our department who are trying to recreate something, or who are trying to set this up, where you can actually set up some optical lattice, a standing wave, in which you can trap these atoms, and then each of these atoms so people usually use alkali earth atoms, because there you can just engineer a decoupling between the nuclear and electronic degrees of freedom. So the nuclear degree of the nuclear spin can be pretty large. So for strontium, it's already 3 halves. So you have 4 states, and that results in SU4. and so those atoms are loaded onto this lattice, and now for spin half, for SU2 spins, or spin half, there are two choices, right? Up and down. Now there are four choices. Let's call them A, B, C, D. Okay. And now you can form singlets in the same way. Earlier it was just up, down, minus, down, up, because there are only two possibilities. Now I can have AB minus BA, CD minus DC. There are 6 combinations because 4 choose 2. Right? There are 6 combinations. And now these 6 combinations, once you put them on a square lattice, they can actually pair up, which means that this can pair up with that, forming a singlet of SU4, which means something that involves all 4 colors. Right? And so you get these kind of configurations, right? And these are called valence bond states. These, and they point in one direction, either they point in X or they point in Y, or minus X or minus Y. So there are 4 directions. But again, in this system also you can recover something like a circle. So you get if you look at these valence bond solids close to a phase transition, you see that you recover a full circle, just like we saw for the classical.
But is there a mapping from this model to the clock?
In the sense that not directly, but at the level of the field theory, of course. Yeah, there is. Yeah, because you have the same. The thing that you need is to check whether the domain walls have some preference, because there also it was it was energetically favorable to have this next to this and not this next to this. And again over here also you have the same thing. Yeah, so this is another case with completely different physical system, but you see the same physics over here also. Okay, so that was okay. So now that was all about equilibrium. So now moving into dynamics. So for dynamics, one of the very classic theories that we use all the time is fluid dynamics, right? We know that even though water is made out of very tiny molecules, we don't need to treat it as tiny billiard balls, right? We can just treat it as a fluid, and there's an entire mathematical framework for it which works very well, and in some sense that is emergent, right? Because it works only because there are a large number of molecules. If you go down to a level of 2 or 3 molecules, hydrodynamics is not going to work, right? So now we are looking at something similar for magnets, where you take a very large configuration. So this is some configuration of spin up and spin down, right? So black is spin down and white is spin up, let's say, and you have some kind of a constrained rule where they can only move along with their partner. So if there is a spin up here and a spin up here, then they can turn into that, right? So this is something that is actually engineered already in trapped atoms, and this has also been seen in insulating crystals, things that were explored for superconductivity, where this kind of a correlated hopping was seen. So here, this is the Hamiltonian basically, that it creates a spin here, destroys a spin here, creates annihilates and creates on the others, right? So this is pictorially what it's doing. So here the dynamics of this is very interesting, right? Because if you start with something like this, which is a very artificial state, where there are stripes, so there's all spin down, all spin up, all spin down, all spin up. You have these kind of stripes. This is completely inactive, because under this rule, nothing's going to happen to this, because there's not a single, if you zoom into this and look on the border or anywhere, there's not a single placket that looks like that. So this is completely frozen. So there's no dynamics. But now let's make it a bit weaker, because this is a very microscopic configuration, right? You have to really zoom in and have sharp borders and so on. Let's make it weaker. Let's make something that's macroscopic. So here I just have what's called a density wave. So I have a slow variation of spin up and spin down. So there's some region where it's spin up, then spin down, and spin up and spin down, right? So it's like that. And now what happens with this? So when you have a configuration like this, we are going into the regime of water with large number of molecules. So now hydrodynamics should apply, and we can do a calculation with mean field theory calculation and so on, which will give us some relationship to hydrodynamics, which says that this wave vector k to the 4th times t should be a constant. So this is very similar to, so diffusion would just have k square t. If you might have seen already in your StatMech classes that if it has distance traveled goes as square root t, right? So that corresponds to k square t when you go to Fourier space, and this is called subdiffusion. So it's k4t. It's slower than diffusion, and it goes into into this form. But anyway, we have some equation, right? But the interesting thing is that even for these configurations, you don't really see this. You see something that is much slower. So over here I'm getting powers which are like k to the 18 or something like that. So something that's continuously changing. So this kind of very strongly constrained dynamics is creating something that is somewhere in between hydrodynamics and some microscopic description. So this is this is a completely numerical study, and I'm still pursuing this as to understand it better. But there's some ideas over here that these particles cannot move freely because they can. So here I have a configuration where there's a lot of active plaquettes marked by stars, and the moment one of these flips, then I get something I get one hole that moves to the next line, but it's not able to move further. Right? So it's very different from diffusion. Diffusion, which is how we model a lot of these relaxation processes. You have one particle and it's moving in space, Brownian motion, is getting knocked around, but it can move anywhere. It's not constrained as to where it moves. Right? Here that's not the case, and that's what is causing all of this complication. Right? But it's so this is a smooth way of interpolating between random configurations and very pathological.
You go from there to that, I mean, you put on a temperature or something? Or what?
Here,
Yeah.
so I just start with this configuration and then I use this dynamics.
Okay.
And given enough time, it will relax to random.
To a random.
Yeah, because it's a thermalizing dynamics.
Right.
So it will. Yeah. But the question is how long, because from hydrodynamics we get some idea.
So the closer you are to that perfectly frozen state, the infinite amount of time it takes.
Exactly.
Right.
Yeah. Right. But there's but there are universal powers over there about how it goes, which are depending really on the wave vector rather than how close you are to this. So if your wave vector is very wide,
Right.
then you get something that's extremely slow. Yeah. So that's a bit.
So why is that?
So that is because whenever you have a large disbalance,
Yes.
which means you have a large white patch or a large black patch, that acts as a wall, and it doesn't thermalize very quickly.
Okay.
So that is a sort of microscopic explanation, but still we have no explanation about how these very high powers are coming about. So that's one example of dynamics, and then another example of dynamics is very interesting mechanism of spatial fracturing, where consider a bilayer. So this is every dot over here is a spin, and I have two layers of square lattices, right? And now there's some interactions. I'm not going to specify what the interactions are, not required. On each rung, so this is a rung, there are 4 possible states, right? Because each of these can have 2 up or down, so 2 times 2, 4. So you can have up on the upper layer, up on the lower layer, and you have 4 possibilities. Now I can actually engineer some interactions such that if I have this state, which is up and down, that does not affect sites with up down and down up. So there is a dynamical separation where, so this happens because there is a conserved quantity. So there is this conserved quantity which is saying that sigma z of upper and times sigma z of lower is fixed, it doesn't change, and it's not affected by the Hamiltonian, so it's either +1 or -1. And so for these guys it's +1 and for these guys -1, and it's, you can just understand it as whenever it's +1 it doesn't talk to the -1 guys. And there is a variety of frustrated magnets where you can engineer this. Right? They are very fine-tuned points because if J2, J1 have to be chosen in a very particular ratio and things like that. But still, this mechanism is there for these models. And the interesting thing is that now, based on whether this is +1 or -1, you get regions. So this red is all where they are +1, and blue is where they are -1, and so on. And now if I perturb this a little bit, what that means is I change this alpha plus beta to alpha prime plus beta prime or something like that. Then that disturbance will spread out along this patch, but will not affect patches nearby. Yeah. So I had actually a video on my laptop, but my laptop wasn't able to connect to this. But the video is just about waves propagating. So just imagine that this is a plane, and on this plane you have some fracture where this entire region is red and this entire region is blue. And I make some disturbance that propagates as a wave out, but it reflects from the boundary and comes back in. Right. So that's exactly what will happen over here. If I make a disturbance over here, the wave can only propagate in the red region, and it cannot go outside of that. So, and the interesting thing is that this is nothing to do with spatial structure. It's not like the spatial structure is broken, which is why this is happening. This is happening just because there's a degeneracy which is saying which is creating this, that these basically spins that have this kind of state do not care what their neighbors are doing if they are in this kind of a state. So this I can talk about the details, but yeah, this is just broadly what is happening here. So yeah, so that was I think I talked about 6 or 7 different projects, so it should perhaps start wrapping up. But before that, I wanted to talk about one application. So these days, as you all know, quantum computing is becoming quite a buzzword, and there's a particular style of quantum computing called adiabatic quantum computing, where what we do is you start with some kind of a easy Hamiltonian. What it means is something whose ground state is easy to prepare. So something that's just, let's say, uniform field, where you know that every single spin is just pointing in that direction. And there's a target Hamiltonian. The target Hamiltonian solves some problem. So for example, let me give you a problem. Let's say find the bit string x1, x2 up to x8 such that x4 plus x5 plus x8 mod 2 is 0, and some other constraint and some other constraint and some other constraint. So I give you a bunch of constraints, and you have to give me the bit string that satisfies all these constraints. This is not a trivial problem, and this can also be used to solve real world problems, like the traveling salesman problem or optimization and things like this. So this can be encoded as a spin system, where there are a lot of spins over here, and x4 plus x5 plus x8. So this is x4, x5 and x8. This is going from here x1 to x8. There I put some kind of interactions, and then I get this model. So I start with something that is very easy, where I just have uniform field, and this is my target Hamiltonian, where this is it's encoding this solution, and then I run through this with time. And so the idea is something like this: you start from some state, some energy landscape where the minima, there's just one minima, and you prepare it in that minima, and then you drag it along with time. So this S is just the same as T, and you finally end up in the solution to your problem. And this crucially depends on the nature of phase transitions in between. If you are traversing this and you happen to hit upon a Hamiltonian which has a phase transition, which is critical in the sense that it's at a phase transition, then your answer will be strongly scrambled, and then you won't get the correct answer. So basically, the success of this way of doing quantum computing depends on the physics of the problem, which means it depends on the phase transition. So this is where physicists are coming in to understand these things.
So
yeah,
this connection of phase transition, is it like let's say for an NP hard problem I expect a phase transition, or is there a structure of a computer science problem which will yield a phase transition in the physics lab?
Yeah. So in general, we have seen that people have seen, actually, it's a very big field, that if your problem is very hard, so they are very similar to spin glasses, and that is something where the energy landscape is very rough, and you will always get tons of minima and you get stuck in those, and then associated with that there's a phase transition. But if you take a simpler problem, for example, I showed you this problem, and this problem has a first order phase transition, which means that you have to go extremely slowly to be able to get through to the correct answer. But the very neat thing is that if you replace this with, instead of having 3 bits in each clause, if you replace it with 2 bits, so x4 plus x5, that becomes a trivial problem to solve, and even the phase transition changes nature. The phase transition also changes to something that's continuous, and that is you can pass through that much faster than a first order transition. So it's somewhere it's linked, but this is still an active area of research because it's not 1:1.
And you mentioned D-wave.
Yeah.
So why do you mention D-wave?
So D-wave does this exactly. So D-wave is a set of some superconducting qubits which can encode this, and then they can start with a very large field, equivalent of very large field, which sets it in this, and then they do these ramps. And in D-wave, you actually have control about how you want to change the time, whether you want to change this t quickly at first, or you want to change it slowly, and so on. So and then you can read out the answer at the end.
So there was a lot of controversy whether what D-wave is doing is anything quantum or not.
Yeah, and that's because there is a lot of if you ramp this very fast, then this quantum nature doesn't really matter. and this is, and also then there's corruption from temperature and things like this. So they are actually trying to find some problems which are exclusively going to sort of settle this debate by saying that, you know, if this problem, you can get this answer only if you go via quantum annealing or something. Yeah. So then there was a brief review. I mean, I hope it wasn't too much because it was jumping a lot of topics. I just wanted to give a flavor of all the things that I'm interested in, and you can latch on to whichever one you find interesting, and we can talk about that. So in addition, I just wanted to talk about other broad research interests. So I already talked about non-equilibrium physics, about how systems approach equilibrium. What is the meaning of temperature for quantum systems? This is something that people are still working on. Something you might have heard goes by the name of eigenstate thermalization hypothesis, and to what extent it can be used, whether there are any caveats to that, and so on. And most of my work has been related to numerical methods. So I'm very interested in understanding if physics can guide algorithm development, and in this direction I've been implementing some ideas for the Monte Carlo method and also for tensor networks. And there are some ideas now coming up in the field about using machine learning techniques also for doing this, but I want to get involved in that in the future. And another thing is about what Weber just mentioned, is about how do you really distinguish between quantum and classical features of these condensed matter systems. So one thing is entanglement signatures, and we are trying to work on this, about what is the unique thing that we see in the entanglement signature that will tell us whether something is really has a large degree of superposition or is just one classical state or something like that. Okay, and then I want to talk about internal collaborations, which I've just started now. I'm very lucky that my colleagues have been very helpful in absorbing me into research over here. So one is with Webho, which is working on entanglement in complex quantum systems. This is being led by Adil, and Saurav is involved as well. And for material simulation with quantum circuits, this is Professor Prabha and Professor Narayanan, who have been working on this with Devanshu, who is leading this project, and we are also discussing for this. Let's see what comes out of that. And then one long-term project which is led by Vishnu majorly, has been part of his thesis, and Professor Narayanan, Thomas Voeta, Jose Hoyos, which is about vacancy-driven energy entropy competition. So we find some very interesting phases over here, which can only be stabilized by a very interesting competition of energy and entropy, which is really a very fundamental concept in phase transitions. Okay, so with that, I would like to thank you all for coming and paying attention, and I hope that was useful, and I look forward to discussions. System. So there are two categories over here. One is that we are looking at ground states of magnets. One of the examples is the one which I was talking about, the Heisenberg magnet, because the state is quite complex and it's hard to visualize. And over there, just studying the entanglement structure, because also for the way to actually quantify entanglement is a bit difficult for these systems, because you have a number of measures. You have Renyi entropy, and then there are some other different measures coming from quantum information. And to understand physically what they say about your state, that is already something that has to be understood, because the interpretation is not so clear.
So in complex, you mean, can you give any numbers? I mean,
how many qubits or something? Yeah, so I am thinking of basically for condensed matter, we are mostly thinking in the limit of n to infinity. So we want to think of features that survive when you scale up. And now with what Adil is basically doing right now is looking at transverse field Ising model, which is a very toy model and looking at different sizes, and then looking at what the entanglement does. So there are some nice calculations even from field theory, which is really in the n to infinity limit. which tells you what you should expect for these systems. So I think it's quite different from the photon case, because there it's really talking about entanglement of just two bodies. Right. And it's
come up later, but
yeah.
so in the case of these dynamics that you talked about, right, where you had these blockages.
Yeah.
This is like the dynamic version of. Is it like dynamic version of the Hilbert space fragmentation?
Yeah, basically, yeah. Because once you think about this, this is one Hilbert space fragment, because
Right.
this state is not connected to any other state.
Any other state.
Yeah, but this state is actually connected to many others. It's just that there is some kind of a bottleneck
Yeah.
for going from here to random configurations. So
Right.
it's there's some involvement of rare events and things like this
Right.
over here, which we have yet to quantify.
Huh.
Yeah, but the scaling is very clear. So there is definitely something that about these and these configurations actually are connected smoothly to the random case. So if you start with a random configuration and you put amplitude 0 wave on top of it, or amplitude tending to 0 wave on top of it,
Right.
already you get violations from hydrodynamics.
So is there is there a way that I can think of this in terms of some sort of continuum field theory? Or
Yeah. So
so that's the thing that will probably tell you what's the relation between the time and length. And
yeah, exactly, and that's how this relationship comes about, because this is using a very simple mean field decoupling
Right.
and then doing Taylor expansions
Right.
because you're assuming that it's smooth,
Smooth, yeah.
and then you get this result. So what we need to do is something more advanced by taking into account the fluctuations,
Right.
and then that will hopefully yield these things.
Is there a particular thing which tells you that you get this slope for this condition?
So just
Sets the slope.
is just the amplitude. So
It's just the amplitude.
It's just the amplitude. So if the amplitude, so these are all different amplitude data for different amplitudes, and I can see that each of them is a different slope on a log.
Right.
So this is completely numerical. So right now I don't have any theory justification as to why the amplitude is the one that is controlling,
It's
but
controlling the
yeah,
slope.
yeah. But naively it is just saying something that if the amplitude is high, then you have large patches where you have a huge imbalance.
Huh.
So that is sort of saying that it should be slower, but why should it be qualitatively slower? That is not quite clear.
So just in relation, the next slide had
Yeah.
which is essentially the Ashkin-Teller.
Yes,
It's
of
very
course. Yeah.
Ashkin-Teller. No, so does one know what happens, whether one can get similar sort of stuff if you take an Ashkin-Teller and drive it, where you are stuck in one of the.
Yeah. So that is one way to do it, because we looked at this model with perturbations that actually destroy this exact conservation,
Yeah.
and then you can drive it to recover it.
Right.
Yeah, that is possible. Yeah.
So you have already done this.
Yeah, but it's not exactly the Ashkin-Teller,
Right.
but it's
Yeah,
almost
so
the same.
You don't have the quartic J term.
Yeah, exactly. Yeah, because that comes because Ashkin-Teller is kind of robust, so you don't need exactly that Hamiltonian, right?
Right,
So you can,
right. Okay.
So your the slide on the adiabatic computing. So there are these techniques like the adiabatic shortcuts. We
Yes.
introduce some terms to the Hamiltonian
to get around.
So has that sort of solved any, like this 3-sat kind of a problem ever, or it's just
No, actually, those adiabatic terms actually tend to be then highly non-local.
yes.
Yeah, and that so in D wave that's not possible to implement. I'm not sure whether numerically anyone has tried to see that. Numerically, I suppose you could do it, and then you could look at the gap, or you could just simulate it numerically.
Simulate numerically.
Yeah, simulate numerically and then
Wasn't
see
there a
what is
K-sat problem that Roderick and completed?
using counter diabatic.
I don't know whether they have a counter
Right.
I forget.
Yeah.
Using neutral atom based systems once a max cut, right?
Yes.
This tiny symmetry and
Yeah, because they,
yeah. Things do, which is also using the same principle. It's just not superconducting qubits, but
strapped ions.
neutral atom,
Neutral atoms. Neutral atoms. Yeah, because there you have much higher degree of control on this. What they can do over here is very rudimentary compared to. So basically, if you are, as you are changing your time, your state is traveling along this. So this is your ground state energy, and as you are traveling over here, the probability of getting contribution from the upper states depends on the inverse of this gap squared. So if the gap is small, and if your speed has to be less than 1 by gap square. If your speed is not less than 1 by gap square, then you get contribution from the first excited state. Then when your simulation ends, you might be in the first or second excited state, which means that you are not in the right answer. So the smaller your gap is, the slower you need to go, and the slower you can't go slower because coherence times are bad. So that is a bottleneck, and also practically then it won't beat classical algorithms, right? If it's very slow.
Are there any more questions? If not, I think we should thank the speaker. Thank you so much for your talk.
Thank you.